Assalamu alaikum students. Welcome to our second lab session for the course Digital Logic Design. My name is Ali Roman and this lab is designed for the BCS 3A section. In this lab session we will be discussing the implementation of half-adder circuit using Verilog HDL. So let us first see the content we will be covering in this lab session, and later on at the end of the lab we will be having a demo. So first of all, we will be having the theoretical background of the adder circuits. What are the adder circuits? How adder circuits work? And we're going to see with some examples. And then after covering the theoretical background, we'll switch to the demo by using the models in software. As far as the reference readings and acknowledgements are concerned, this is still chapter number 3 of the digital design with introduction to Verilog HDL. So we are following chapter number 3. So as far as the address are concerned, this is basically the content which we have extracted from our first class, that is the design example to the basic adders. So in the computer systems, a variety of adder circuits are used in order to perform the arithmetic operations. The most basic arithmetic operation is the addition of two binary bits. For example, if we add 0 with 0, let me see, we have some pointer, yes. So if we add 0 with 0, the result is 0, the sum result is 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 1, 0, where this 0 is the result of sum and this 1 is the carry that is produced by adding two numbers with the maximum value. This is basically the carry. So here this plus operation is not a boolean operation, this is basically the arithmetic operation that represents the addition operation. So the first three operations produce the sum of one digit, but when both augment and addend bit are equal to 1, that is the maximum value at the single placement for the binary numbers. The binary sum consists of two digits. The highest significant bit of the result is called the carry bit. So this 0 is basically the sum bit and 1 is considered to be the carry bit. So let us first see what the half-adder circuits are. Let us revise the concepts of the half-adder circuit. Half-adder circuit is a circuit that has the capability to add two binary bits. Here x and y are the two binary bits that are being added to produce the result of sum and carry, where s represents the sum result and c represents the carry result. So the input variables designate the augment and addend bits. Here in our example, x and y are augment and addend bits, and the outputs are s and c that represent sum and carry, which are also explained in the last point of the slide. So we have to design a circuit. We have to describe our design, which have the two respective inputs, that is x and y, and two respective outputs, that are s and c. And the name of the module should be the half adder. So let us see the content and truth table, how the half adder performs the addition operation. Here x and y are the two input bits and c and s are bits. Basically c represents the carry bit and s represents the sum bit. So if 0 is added with 0, the sum result is also 0 and carry result is also 0. If 0 is added with 1, the summation result is 1 and no carry is produced, so carry is equal to 0. If 1 is added with 0, so the summation result is 1 and the carry result is 0. And if both the bits x and y are equal to 1, for example x is equal to 1 and y equals to the 1, now the sum result is 0 and carry result is 1, that is 1 0, the binary of 2. So this is basically table 4.3 of the book for the adder circuits. Now if we see the logic implementation of expressions, the boolean expressions obtained for the sum and the carry output, we can see that sum expression is equivalent to x y complement or x complement y, and carry is equal to x y. This is the standard sum of min-terms expression, or the canonical form, we can say that. So if you observe that summation expression, this is basically the expression for the exclusive OR gate. So for the sum expression to be evaluated, we can say that we have to use one exclusive OR gate, and for the carry expression we have to use one AND gate. So we can either implement this setup by using one exclusive OR gate and one AND gate, or we can implement by using the primary gates and OR. So we can have both options to implement. So let us see how we're going to implement this by using the Verilog HDL. So let us now go to the software and the demonstration. In this software, in this demo, basically I'm gonna give the basic skeleton of the code of the hardware in the hardware descriptive language using Verilog HDL. So what you have to do is, by using the same structure, you have to implement your design, and you have to simulate your design, and you have to submit your report into the groups before the commencement of the next lab. So you have to verify the operation of the half adder circuit. Either this circuit has the capability to add two binary bits or not. So you have to prove that. So let us go to the software. So this is the primary interface of the software. Till now, I hope so you all get familiar with the software as well. So what we have to do is, to start the lab, we have to create a new project. So what I have to do is, please follow these steps. So we have to create a new project. So go to the file menu, new, and pick the option of the project from the sub menu. If any project is open, this will close the current project. We will continue with that. So now, first of all, what we have to do is, we have to name the project. So I'm giving the name as lab 2. Now, where to save this project? I'm going to create a new folder here in a C drive, for example. In the C drive, make a new folder, and I'll name it as lab 2. And I'm going to select that folder and select OK. Now the default library name should be work, and the copy settings are from modelsim.ini from the installation folder, and we're gonna say that copy library mappings, and we're gonna click on OK. Now we have to add some files in order to describe our design. So I'm adding a new file, and the name of the file is, for example, half adder. And the type of the file is Verilog HDL, and I'm gonna press OK. Now this file is added, and I'm gonna file another file that is basically the test bench file. So I'm naming it as t underscore half adder, and the type of the file is Verilog, and I'm gonna select OK. So till now, what we have done is, we have created a project with the name lab2. Then we have added two files in it. One for the half adder to contain the description of the half adder, and one is a test driver of the module that is going to use to test the description which we have designed for the half adder circuit. Now open the half adder file. So what we have to do, first of all, we have to define a module with the keyword module, and then the name of the module, that is half adder. So what we were doing is, first of all, we have to define the module, and we have defined with the keyword module, and the name of the module is half adder. Then the next step is, we have to define the ports, the connections which are used to communicate with the internal design. So the inputs were X and Y in the previous description, and the outputs were S and C. So till now we've just defined the ports, the keywords that are used for the ports. We haven't specified what are the inputs and what are the outputs in this particular design, and we're gonna end this module with the keyword and module. And then the next step is to define our ports. What are the ports that are used for the input and what are the ports that are used for the output of the design. So we start with the keyword of input, and we are saying X and Y are the inputs of the design, and the outputs of the design are S and C. Now what you have to do is if any sort of wires are required for the interconnection, you have to define wires here in this area. Define your wires for the interconnection of gates if required. So we have to define wires here if there is any sort of interconnections required between the gates. So you have to define wires in this particular area. Then the next step is implement your, or you can say that describe your design functionality here. So students, what you have to do is you have to create a module with the name half adder, define its port list as X, Y, S and C. X and Y are the inputs, capital X and capital Y, because this is a case sensitive platform. So S and C are defined as output. Then if any sort of interconnections are required, you to describe the wires here. If no interconnections are required, then no need to define wires here. And then in this section you have to define the functionality of your module, and then you have to save the module. Now coming to the test bench file, we have to define a module t underscore half adder semicolon and module. Now the next step is you have to define your inputs as reg and outputs as wires that are being used for the communication with the main design that is under your test. So we are using the keyword reg, X and Y variables as registered inputs, and wires, sorry, the keyword Y, S and C, semicolon. What we are doing here is define your input connection of the module as type reg, and define wire, or you can say that define the output of your module under test as wire connections. We can also use different names as instead of X and Y and S and C, but we have to know that how we're going to connect those different names to the respective inputs. For example, I am saying that this is A this is B, this is C, and this is D. So when I'm going to call this module that is under test, that contains the description of the half adder circuit with the keyword with the name that was half adder, its instance name, and then I'm going to connect those respective ports. For example, first of all, our module contains the input, so I'm connecting A and B here, and C and D here. So whatsoever the inputs are applied to the circuit, this A is connected with the X input, this B is connected with the Y input of the module because we are using the same placement, and this C is connected with the S output, and D is connected with carry output. So in order to avoid the confusion, what we are taking the ease of using the same variables that were used, or the same keywords that were used in the respective module. But we can also do that also. So I'm just commenting this step. So I'm also commenting this, I'm also commenting this, and I'm using the same words, veg, x and y, to avoid any confusion, and wire S and C, and I'm gonna instantiate the module just before which I have instantiated the module half adder. So I'm writing the comment here, so I'm using half adder with its instance name and the respective port list, semicolon. Now what we have to do is we have to provide the instances. For example, X and Y, we provide the inputs in order to evaluate our design, to evaluate our description, to produce S and C. So we're going to use initial block, initial, and we'll start with the keyword begin, and end, and then we'll provide the respective inputs. For example, I'm saying X equals 1 tick, B 0, Y equals 1 tick, B 0. Then after having a time delay of, for example, 200, I'm defining X and Y as 0 1. Then after again producing the delay of 200 time frame or time units, I am flipping the inputs to 1 and 0, and then again with the delay of 200, I am making X and Y equals 1 1. So your test bench is ready for the evaluation process. So what I'm doing is right now I'm just deleting this instantiation process to see if you can define your inputs and outputs properly. So what you have to do is, first of all, define wedge and wires, according to your design. Then the next step is instantiate your design. And the final step is to provide the combination of inputs that are required to evaluate your design. So in this lab session, you to create these two files. One is a design file with the keyword half-adder.v, and you have to describe the design functionality. Save that file, compile that file to see any sort of errors. If no error exists, your compilation is successful. Then the next step is to design your testbench module with the name t_half-adder.v. First of all, you have to define the reg and wire according to your design parameters. Then you have to instantiate your design that is under your observation or test. Then you have to provide the following input combinations in order to generate the timing diagram. So as far as the lab report is concerned, what you have to do is you have to provide this description as well as the snapshot of your timing diagram, uh, and you have to submit that lab report before lab 3. So this is the deadline for the lab report. So you have to submit in a short form. You have to create a Word file that consists of your verilab description of these two files, and with your group members and the details of your group members, and also your simulation results, that is basically a timing diagram, and you have to explain that timing diagram as well. So I hope so till now the confusions are over and you are familiar with the design process of digital modules using Verilog HDL and how to use this tool. And we are still on the gate level description. We haven't started any sort of data flow description or the behavioral description. So if we got some time at the end of our labs, dedicated labs, we're gonna switch to the behavioral descriptions as well.